Good afternoon, everybody, and welcome to the Frontiers of Brain Health. In this series, we bring in innovative and interesting speakers who are leading-edge researchers who are informing us about the future of brain health in a variety of different ways. And this year, we do have an emphasis on innovation, on forward-looking research, and research that can help us to future-proof our society. And you'll see that increasingly throughout this coming year. The talk is virtual as well, so welcome to the virtual audience, and we will have time for questions at the end. If you are a virtual audience member, please use the Q&A, and we will get to some of those at the end of the talk. And today we welcome Dr. Gopal Gupta. Dr. Gupta is a professor of computer science at UT Dallas. He's also the co-founder and co-director of the Center for Applied AI and Machine Learning. Very timely work in that lab. He has a PhD in computer science from UNC Chapel Hill. From 1989 to 1991, he worked at the University of Bristol in computer science with David Warren, of the Warren Abstract Machine fame, for those of you that have been following computing development. He was also on faculty at New Mexico State prior to coming to UT Dallas in 2000. He won the Outstanding Computer Science Teacher of the Year award in 2008 and was department head for 11 years, so a real fixture in our computing space at UT Dallas, and has served as president of the Association for Logic Programming previously. His current work includes automated common sense reasoning, explainable AI, logic-based software assurance, goal-directed answer set programming, and co-inductive logic programming. Some of those terms are regularly in the news, particularly explainable AI, and of course, automating more and more aspects of our lives. He's had support from DARPA, NATO, the NSF, the Department of Homeland Security, the EPA, Sandia Labs, and the Fulbright Foundation, among others. He's founded 2 companies based on his logic programming research, and his co-inductive logic programming work won a 10-year Test of Time Award at the ICLP conference, so having a really large impact for a number of years. And Gopal does fascinating work in the ways that AI increasingly interacts with our lives. AI is constantly exceeding our expectations and increasingly exceeding our abilities. So working with AI, teaming with AI, evolving with AI is quite literally one of the most important things we're going to do with the rest of our lives. So let's go ahead and welcome Dr. Gopal Gupta.
Thank you so much, Dan. It's a great privilege and honor to be here. So you can see my title, and also thanks for the generous introduction. So let me, acknowledge all the PhD students and members of my lab, postdocs, and others who actually worked with me for the last 35, 40 years that I have been working in logic and AI and related areas, and of course, support from many of the funding agencies. So let's get started. So I'm a professor, so I like to profess. So probably I have more, content than we have time for. So we might skip a little bit, and I will even show you some code, and hopefully you can follow it because it's, high-level logic. So, okay, so let's talk about artificial intelligence. So intelligent reasoning by computers has been a goal of computer scientists ever since computers were first invented in the 1950s, right? So first computer was built around 1957, 58, and as soon as this computer is built, people start, talking about how to build applications that are, human-like. So game of checkers was the first one to be programmed. So the question is, what is intelligence, right? That's the question you want to ask. So I'm not going to, wait for you to answer. So I would say argue that intelligence has 2 broad components. So the first one is that, we can acquire knowledge, we learn. So we might see patterns, and based on these patterns, we generalize. So that's basically learning. And if you mechanize that, you automate that, that's called machine learning. So for example, a child might observe that if they drop a mug on the floor, a ceramic mug, it will break, might do it 2 or 3 times, and then figure out that, okay, if something looks fragile, ceramic, don't drop it. But then you might even learn that if you drop it on a soft surface like a carpet, then it does not break. So once you have learned from these patterns, and then that you essentially learn this knowledge that sits in your mind, and then you use this knowledge for reasoning. So once the child learns that dropping the mug will break it, next time the child will actually use that rule sort of that internalized in their brain. So that is reasoning. And if you automate it, that area is called automated reasoning. So there is, of course, vision, speech processing, speech generation, etc. But by and large, you can say that intelligence has 2 components, learning and reasoning. So, of course, AI has been receiving a lot of attention lately for the last, especially since the advent of ChatGPT, maybe 2022, it's kind of exploded. So, and then when people say AI, what do they mean? So AI has become sort of synonymous with machine learning or deep learning, and today maybe with generative AI. So if you look at the history of AI, then for the first 40, 50 years of the history of AI, when people said AI, they actually meant reasoning. So of course, today the pendulum has swung the other way, and when people say AI, it actually means learning. So research on both strands started in the 50s, so a little bit of history. So what is machine learning? So the idea is that you're given background knowledge, some background knowledge, and you're given positive and negative examples of a concept, what is called training data, and then you learn the general rule or function that captures the concept, that's sort of hidden in that data, or what's called the model. And then once you learn the model, what's called a model, right? You use it for prediction. So for example, you might learn based on examples of, you want to learn the concept of a bird, you're given positive examples of what a bird is and negative examples of what a bird is, and then you learn from that, that's what machine learning systems do. And there is all kinds of, machine learning techniques, supervised learning, unsupervised learning, reinforcement learning, etc. Many of you probably already familiar with that. Now, what is automated reasoning? Here, the idea is that you're given pieces of information, what in mathematics is called axioms, and you deduce new knowledge from these axioms or, these pieces of information. Or essentially, you draw new conclusions. So, for example, if we know that all humans are mortal, and we know that Socrates is a human, you will conclude that Socrates is mortal, right? So hopefully you understand the distinction between learning and reasoning. So machine learning has a long history, and I'm going to dwell on this. So Bayes' theorem, which is sort of a cornerstone of machine learning, and many other techniques like perceptron neural networks were actually discovered ages ago. So today you have neural networks, deep learning, large language models, all that basically use the machine learning technology. Automated reasoning also has a long history, starts from essentially discovery of logic and inference procedures. And these go back thousands of years with Aristotle's syllogism, and then ancient Indian work on formalizing logic. Modern logic started in the 1850s, and today we have advanced automated theorem proving systems that can prove mathematical theorems automatically. We have logic-based programming languages, rule-based systems, and all kinds of things. So AI has had a lot of success over the years, and of course there are many limitations as well. And some of you may remember in the 90s, the Deep Blue system built by IBM, the chess playing system that actually beat Garry Kasparov in the game of chess. Garry Kasparov was the world champion back then. Some of you might remember. So that was purely based on reasoning or search, essentially. No machine learning, no learning involved. Then in 2012 or so, there was the Watson system that was again built by IBM and then came on Jeopardy and beat the 2 top champions of Jeopardy. And Watson actually was based on both learning, machine learning and reasoning. So they first tried to build it using reasoning, but that did not work very well. But once they brought in machine learning, then it really excelled and beat the world champions. And today you have systems like AlphaGo or AlphaZero that are purely based on machine learning, or self-driving cars or generative AI. So so machine learning has become more and more prominent, and successful applications have been built using machine learning. So while machine learning in the last 10 years, 15 years has had tremendous success in many applications, it has still many limitations. So what are these limitations? It can give you wrong answers because the model that you learn from data is an approximation. So it all depends on how good your data is. So you can still get wrong answers. And you need, of course, lots of handcrafted data for each narrow application. And explainability, interpretability is a problem. So these models are black boxes. They really don't tell you, how they are making the prediction. So you cannot get any insight, cannot do reasoning, and they're computationally expensive. Whereas we humans can, just use 12 watts of power, but these machines use, so much power. So here are examples of limitations where researchers put a tape on this stop sign, and self-driving cars got fooled and they could not recognize this stop sign. Another example, and again, these are, you might have seen these before, where you take a picture and you put some noise, add some noise to the picture, and now the machine learning system is thrown off. So the most problematic one is the one at the bottom where you have a picture of of a school bus, and then you add some noise, and now the machine learning system thinks that it's actually an ostrich. And there's also problems with explainability. So for example, this is a very well-known example. So you're given pictures of wolf versus husky, and your job is to distinguish between the two. And then what happens is that when you train a machine learning system, then the model that it produces, all it does is it figures out that pictures of wolves have snow in the background. So it just focuses on that. So if there is snow in the background, it says it's a wolf. If there is no snow. But of course, we don't know because it's a black box. So now if you give it a picture of a husky with snow in the background, it'll actually say that it's a wolf. So of course, if we knew that, and as humans, we might do that as well, right? We might simplify things as well to recognize things, and it does happen. But of course, if the model had told us that that's how it's recognizing, we would know, but it does not. So it can make wrong predictions. So speaking again of limitations, you have autonomous vehicles, prominent technology that is used is machine learning. And then of course there are many problems. So today's, for example, these autonomous cars like Tesla. So there's a scale that has been designed by the Society for Automation Engineers that measures the level of autonomy that goes from I think 0 to 5. So Teslas today are at like 3.5. Now, a lot of promises were made, and the problem again is that they use machine learning, and if something, they've not been trained on something, then it won't be able to recognize that part, and it won't work, and that's why you see some crashes and things like that happening. So again, I won't go into the details where many people who got into, started companies around autonomous vehicles and stuff, and then got disenchanted. So the one quote I want to point out is that we were promised full autonomy by 2018. This was in 2015, but then in 2022, Tesla argued in court that this promise was just a failure, not a fraud, because they were sued for that. That was a fraudulent promise that was made. So again, the problem is that that machine learning systems, have limitations basically. And then, of course, you have generative AI systems that all of you are familiar with, large language models. I'm sure everybody has used ChatGPT. And, again, fantastic technology. It can generate poems. And so I was giving a tutorial to Marriott folks, on AI, teaching them about AI. And then I asked it to write a poem about how great the Marriott chain is. And it wrote a nice poem over there. It can generate pictures. And, you can ask it to, for example, generate a Egyptian-style painting of two people arguing over whose turn it is to take out trash, and it will draw this nice picture. So it's really a fantastic, right, technology. So large language models, so how do they work? So quite remarkable, right? I'm sure all of you are impressed. Quite remarkable. How do they do it? So you can think of it as sort of an example-driven search where it has a huge number of examples. It's like you trying to learn to play chess, but you don't learn the rules. You have access to millions of traces of games, of chess games. And then instead of actually using the rules of chess, you look at these these traces of games to figure out your next move. And that's what they're doing. So given an incomplete sentence, large language models try to predict the next word that would reasonably fit. And what is a reasonable fit? What someone may write after looking at billions or millions of sentences. So for example, if I have the sentence, four scores and seven, what's the next word? All of you know years, right? So that's what they're doing, except that they've analyzed all the text that is out there on the web, and then build these giant probability distribution tables that basically tell it, if you have these 4 words, what's the most likely 5th word and 6th word and 7th. And that seems to work amazingly well. So of course there are many limitations because, again, as we all know, these large language models hallucinate. They give you wrong information. And my most favorite example, so I had other examples, but one of my most favorite examples is this one, where you say, draw me a picture of a clock with hands at 3 p.m. Now you know that most pictures of clocks will show 10 past 10 because it's aesthetically pleasing. So doesn't matter what you ask, it will draw a picture showing 10 past 10. So if everybody on the web said 2 plus 2 equals 5, then ChatGPT will tell you 2 plus 2 equals 5 because that's how it works, basically pattern matching. So the question is, can large language models, so there's all this quest for artificial general intelligence or intelligence that is as good as humans. So can machine learning and large language models achieve artificial general intelligence or even artificial superintelligence, which is the singularity where artificial superintelligence is intelligence that surpasses humans, and then people warn us about it, right? So can large language models be trustworthy? Can they stop hallucinating? So the answer actually is no. Large language models lack awareness because they're purely pattern matching devices. They don't know what they know and don't know because they're basically just predicting the next word. Unlike us, that we're extracting knowledge from the text or or whatever sensory input that we get. So machine learning really is akin to sensing or pattern recognition or pattern matching, essentially. Right? It's basically pattern matching. And if you look at, so we use pattern matching as well as humans, and even animals use it. So if you look at nature, so nature has made, right, a lot of use of this sensing and pattern matching and pattern recognition. And in fact, non-human animals are much better at it, much better at sensing. So eagles can see better. Dogs can smell better, so they can process. Camels can smell water apparently 50, 60 miles away because water produces some kind of bacteria that travels through air and they can actually sense it. But animals lack advanced reasoning capabilities, as in deductive reasoning, inference-making capabilities. And as you go up the evolutionary chain, right, ending up in us humans, where the reasoning capabilities improve, you see that the level of intelligence keeps getting better and better, and you could say culminating in us humans. So I want to show you a video where there's an albatross. So see how animals just work by their instinct. So if I can find the cursor, okay, so the cursor is missing. Can we click on the video? Okay. Oh, the cursor is here. That's why. Okay, now I know. Okay, so now.
More parents are returning to the colony.
Sorry. Can we double the speed?
Something is not right.
1.5x.
The nest should not be empty.
1.5. 1.5.
The chick is actually right below its parent, but because it's not on the nest, the parent doesn't recognize it. And doesn't help it. Strangely, perhaps, these albatross do not recognize their chicks by sight, sound, or smell. They identify them by finding them on the nest. So these violent storms have created a problem that the albatross are not equipped to solve. If it is to survive, the chick will have to get back on the nest by itself. The chick has made it. The bond is re-established immediately, and its parent once again provides the warmth that the chick so desperately needs. It's safe for now.
Okay, we can exit. Okay, all right. So you see how, it's purely instinct driven, pattern matching. So whereas if this was a human, you would say, well, my baby is missing, must be somewhere around here. You'd actually go look. But you saw that the albatross actually did not do that. So the point is that you need reasoning as well for intelligent behavior. So essentially, better reasoning capability means higher intelligence. Now there are two different ways in which, coming back to the title of my talk, slow thinking. Two different ways in which brain processes thought that you already might be familiar with from this famous book, Thinking Fast and Slow, by Daniel Kahneman. So the brain processes thought in two different ways, what are called system 1 and system 2 thinking. So system 1 thinking is intuitive, fast thinking based on recognizing patterns and using our senses. And system 2 thinking is slow deliberative thinking based on reasoning, or I would say common sense reasoning. So I think the video is still running, maybe. Oh, there's a plane. Okay. System 2, slow deliberative thinking based on common sense reasoning. So think of, for example, you hear the siren go on during inclement weather. Then you recognize the siren using your system 1 thinking. Basically, you match the pattern. And there is no way to actually describe the sound of a siren, right, to someone. You have to hear it, and somebody has to tell you, well, that's a siren, right? So you hear the sound of a siren, and the weather is inclement weather is bad. In North Texas, right, where we live, we know that a tornado is coming. So that was system 1 thinking. But then once you recognize that, you have to act, to save yourself. And then you'll start thinking, what is the safest part of my house, right? And then you have to find the space where, maximum number of walls between you and, the outside, and so on and so forth. And that actually requires this deliberative thinking or reasoning, right? So fast thinking can be thought of as just obtaining sensory input, and then we use our instincts to draw conclusions. Whereas slow thinking is basically complex reasoning that we can explain, that we can verify. And of course, so fast thinking is easy because, pattern matching, I can recognize a chair, no effort, a table, I can see you all, right? I don't have to make any effort. But actual thinking or reasoning requires a lot of effort. And in fact, most people do not want to think. So system 2 thinking, people basically are lazy when it comes to system 2 thinking or slow thinking. So if we automate system 1 thinking, it's basically machine learning. Automate system 2 thinking, we have automated reasoning or common sense reasoning. So here's another interesting thing about that, the folks in building these large language models and generative AI systems claiming that will get us to artificial general intelligence. So recent neuroscience research shows that language does not appear to be a prerequisite for complex thought, and language is more of a communication tool rather than for thinking. And in fact, the area of the brain where reasoning happens is actually separate from the area of the brain. And many of you are brain scientists. Probably know this better than I do. So the part of the brain that processes language is different from the part of the brain where thinking and reasoning goes on. And both of these co-evolve. So the point is that you do need reasoning for intelligent behavior, human-like intelligent behavior. So just language processing, like what large language models do, is not going to get you to AGI. So how do you build reliable AI systems? So if we build systems using machine learning alone, then you have this problem of, right, that the function that we learn, the model we learn is approximate. We cannot give any guarantees. So how do we build systems that are reliable, that will get us to artificial general intelligence or that are human-like? So we emulate the human. So if we look at how we work, right, we take all this sensory input, sight, sound, smell, touch, taste, text that we read, and then we actually extract knowledge from it, right? And this knowledge resides in our mind. So I'm looking at the scene and, I have converted this into knowledge that, I see a chair here or a table there. And if you ask me questions about position of this chair or, if that chair over there is to the left or to the right, I can answer all those questions. That is because I have extracted the knowledge and that knowledge sits in my brain. And I can actually check the consistency and completeness of this knowledge through reasoning. And of course, we've also acquired a lot of common sense knowledge over the years, right? A lot of knowledge sits in our mind. So for example, we know that a chair has maybe 4 legs. It has to be stable. It has to sit on a horizontal surface and so on. There are lots of these things that we have acquired that sit in our mind. So we use this knowledge to check the consistency of what we are seeing. So if I, for example, tell you I have an 8-foot tall daughter, you immediately know that I'm lying because, right, you have the knowledge. You extracted the knowledge that, I'm talking about my daughter and that, I'm claiming she's 8 foot tall, and you know that people are not that tall. So immediately you know that I'm lying, right? So you did a consistency check. And then, of course, if our knowledge is incomplete, then we look for more information, right? So again, we have to have a way of judging that knowledge is incomplete. So once we have checked the consistency and completeness of the knowledge that we have extracted, then we will draw conclusions and maybe take actions. So this is the process that we want to emulate. So we use machine learning for converting sensory input into knowledge. So there are all these wonderful machine learning systems have been built, including large language models and vision systems. So we can take all that and we can use these machine learning systems to convert the input into knowledge. So this knowledge is represented using logic or logic predicates. Hopefully, you have some familiarity with logic. And then I can represent the common sense knowledge that we have as well using some kind of formalism, again, logic. And then I can use my common sense knowledge to check that the knowledge that I acquired through my senses, that these machine learning systems are generating, is consistent and complete. And then I can draw conclusions and take actions. So you can think of this as sort of realizing this computational representational understanding of mind that cognitive scientists have proposed. So again, what we're trying to do is emulate how humans think. Now, I'm not claiming that this is how the human brain works, but the idea is that we can build systems that that can perform as well as a human, that essentially, could say a step towards artificial general intelligence by essentially, adopting this approach where we use machine learning only for converting sensory input into knowledge and then processing this knowledge using automated reasoning. So the current approach in AI is to tackle everything at the system 1 level or using machine learning. So if you want to build a question and answering system, say, given a picture, given a question, can you answer? For example, given a picture, you want to know how many, apples are there in this picture. Then the way people build these systems is that they collect millions of pictures. For each picture, there are 5 questions and 5 answers. Throw it to a machine learning model, and the machine learning model learns the associations. Then if you want to answer a question about another picture, specific picture, then you present that picture to the model along with the question, and then it uses pattern matching to answer the question. And many times that doesn't work because we already talked about limitations of machine learning. But instead what we would do is we take the picture and convert the information in the picture into knowledge, into logic predicates. And now I will use reasoning to actually answer questions. And now you can attain 100% accuracy and guarantees and all kinds of things. So for building trustworthy AI systems and achieving artificial general intelligence, we should use machine learning for automating system one aspects. And machine learning is very good at pattern matching, which is what system one thinking involves, and use automated common reasoning for system two. And this way you can have accountability, justifiability, explainability, trustworthiness, whatever you want, right? So the road forward for artificial general intelligence and building trustworthy AI systems is to emulate humans, I would say, and use machine learning for discovering the knowledge in sensory input. And that's basically the awareness that we have, right? Awareness is knowing that this chair is over here and this computer is in front of me, right? I'm representing all that as knowledge in my mind. And then use automated common sense reasoning for processing this knowledge. And processing means checking consistency, completeness, using reasoning, and then drawing conclusions. So now the question is, how do you automate common sense reasoning? And that's something that people have worked on for last, 60, 70 years. How do you automate this slow thinking, right? What we called. So why do computers have trouble in reasoning? So of course people have been working, but there's still no satisfactory solutions. So why do computers have trouble in reasoning while humans can reason about things effortlessly? As I said, human brain uses just 12 watts of power because we have a sophisticated brain and a sophisticated reasoning mechanism, and we can actually draw conclusion even when our information is incomplete. So we use what's called non-monotonic reasoning. So as information changes, we change the conclusions that we so if we drew a conclusion earlier, we might change that conclusion later. So for example, if we get contradictory information, then in classical logic, everything breaks down. The moment you have contradictory information, classical logic says, well, everything is true and everything can be proven false. It just breaks down. But our logic, which is non-monotonic logic, does not. Only the parts of the knowledge that are inconsistent are sort of excised away. We also jump to conclusion. We use what are called default rules. So we jump to conclusion. So if you ask me, can I get to my home? Then the answer is yes, I can get to my home. But you don't think about, there are many ways in which things that can happen that would prevent me from getting to my home. Right? There could be flood, or there could be an earthquake, or somebody might launch a missile that lands between, right? So there are many, but we don't consider those. But as they arise, we consider those exceptions. So we use default rules. So that's how actually we represent knowledge in our mind. We represent them as default rules. So for example, if I can't tell, I'm in my house, can't tell if it's cold outside, I will just look outside and see if anyone is wearing a jacket or not. If no one is wearing a jacket, so it's warm. But maybe those people were from Finland or something. And so there are exceptions, but we deal with those exceptions, right? We also do not pursue lines of reasoning if it leads to some kind of global inconsistency. So for example, we know that a person cannot sit and stand at the same time, right? So we avoid inconsistencies. Also, we have invariants. We know certain things are invariant, and we make sure that those are not violated. So for example, we know that a living person must always breathe. So anything that violates that, we're not going to pursue that reasoning. We can also deal with multiple possible worlds. So that's basically, we can do what's called assumption-based reasoning. So for example, if I ask you, can Nemo the fish talk? What are you going to answer? Well, in the cartoon world, so there are actually two possible worlds. The cartoon world, Nemo the fish talks. But if you have a pet fish called Nemo, in the real world, Nemo the fish does not talk. Right? So we can deal with these multiple possible worlds, and these possible worlds may be inconsistent with each other, right? In one world, Nemo can talk, in another world, Nemo cannot talk. So we can represent, we can work with all this, kind of contradictory things, but logic, classical logic cannot. So we use non-monotonic reasoning, which is, we also use non-well-founded reasoning, and I'm sorry for the technical terms. And you can actually realize these things, So now after decades of research, we know how to automate non-monotonic reasoning and non-well-founded reasoning. So to do that, actually, so a little bit technical now. We make a distinction between what's called classical negation versus negation as failure, and then you'll recognize that actually. So classical negation is where you're reasoning about something, a negative phenomena. So in our code, we'll represent it as minus p. So for example, if I say minus sibling John, Jim, I'm representing the information that I know for a fact that John and Jim are not siblings. And basically, I must have a proof in this case. I must be able to show that John and Jim have different parents. Okay? So an explicit proof of falsehood of a predicate P is needed. And we actually do that sometimes, right? We will establish that something is not true. But there's also this negation as failure, what is called negation as failure that we use. We'll represent it as not P. And this basically involves, so if I want to establish the truth of a predicate, then I will try to prove it. But if I fail, then I'll say, oh, it's false. So now I try to prove that John and Jim are siblings, but I have no information about John and Jim's parents, for example. Then I might say, oh, well, no information. I'll assume that they are not siblings. So we actually do that all the time, use classical negation as well as negation as failure. And of course, we don't realize that. So again, we got to automate all these things now if we want to automate common sense reasoning. So essentially, if we want to prove a proposition P, if we fail, we conclude that not P is true. So essentially, what it means is that if there's no evidence of P, then we conclude not P. So this negation as failure and all this thing has been actually turned into a programming paradigm called answer set programming. And I'm not going to give you, since I only have maybe 10 more minutes. So not give you the details, but basically you can write, we have this programming language that we have designed where you can actually write rules. So let's see if the pointer will work. No, the pointer doesn't work. Let's see if I can make it a pointer. Yeah, so this rule basically says that P holds if conjunction of A1 through AM holds, and I don't have any evidence for B1 through Bn. So we'll skip all this and just show you an example of how you would code something like this. So consider the college admission process where you are admitting students based on if they have a high GPA. So if you look at the first rule, it says if student X has high GPA and it's not an abnormal case, then, so for example, the abnormal case might be the student has a criminal record, for example. Then you say, well, the student is eligible. And then you might also declare rule number 2, student is eligible if student is special, has a special talent, has a fair GPA, and again, you consider exceptions that even though the student is special, has a fair GPA, you may still not admit the student because student has a criminal record. So we can basically model these default rules that we use all the time using negation as failure. And then, of course, we also might say student is ineligible if the student is definitely not special. I have a proof. Student does not have a high GPA. I have a proof. But there still might be exceptions because maybe the president of the university recommended the student even though the student was ineligible. Now, rule number 4 says that if I am unable to prove a student is eligible, I am unable to prove that the student is ineligible, for example, because I don't have enough information, so which means that I don't know anything about the student, then you can write a rule saying, I will interview the student. So you see, I can take a human process that humans use, for example, college admissions, and I can automate that once I have the ability to model negation as failure and strong negation and all that stuff. So what this allows us to do is to essentially have a hierarchy of truth values. So I can basically program P is definitely true by writing a rule establishing what are the conditions that must be fulfilled for P to be true. Now, I can also write something like not minus P, which means I have no evidence of minus P, where minus P means P is definitely false. So you can think of this as P is possible. P may be true because I have no evidence for P being false. And then at the bottom, I have minus P, which I can represent as P is definitely false, not P stands for P may be false. And then if I have no evidence for minus P, not minus P, and not P, no evidence for P, then I know that P is unknown, because neither I can prove it to be false, nor I can prove it to be true. So that's what we actually use in our sort of day-to-day life. And we can actually write rules that say, if something is unknown, then do this. And that's what our programming model should be able to do as well. Now, interestingly, we do not use probabilities in our day-to-day life. We actually use this hierarchy of maybe true, maybe false, definitely true, definitely false, and unknown. Okay, interesting. Think about it. You generally never, if I tell you Tweety is a bird and ask you, does it fly? You're not going to say, oh, 95% chance it flies. You'll say, yes, it flies. But then I tell you Tweety is a penguin, then you'll say, oh, no, withdraw that conclusion. I was wrong. Okay, so you can actually model human judgments and assumption-based reasoning. So I'm going to skip all this technical stuff. You can model obligations, prohibitions. And so we've designed this system called SCASP, which S stands for successor of constraint answers, complicated name. But it's basically a system that allows us to model, represent common sense reasoning automated. And there are many people actually around the world who use it for building applications. And I'll talk about in the remaining 7 minutes, talk about these applications. And we've actually shown that for a lot of things that we use, explanation, deduction, induction, analogy, abductive reasoning, modal reasoning, defeasibility, programming, ethics, you can actually do it in our system called SCASP, freely available. So takeaways so far. So again, I want to avoid the technical details, and I don't have time either. So verifiable, trustworthy, or accountable intelligence cannot be achieved through pattern matching, predictive machine learning, or generative AI alone. If it was possible, then very likely that nature or evolution would have already produced it. So there would be an animal that's is as intelligent as us, but is purely based on sensing and instincts, not based on reasoning. So that we don't see. For human-like intelligence, we need true reasoning capabilities, as in deductive and abductive reasoning. So abductive reasoning is more like sort of reasoning backwards. If you see that your lawn is wet, then you come up with an explanation that maybe it rained last night, or also that your sprinklers got turned on. So you're sort of reasoning backwards, whereas deductive reasoning is reasoning forward. We should be able to perform this reasoning even if the information we have is incomplete. So humans perform non-monotonic reasoning. We should be able to model that if we want to automate that. And essentially, this answer set programming paradigm, which unfortunately I could not spend time explaining, shows how deductive and abductive reasoning can be performed with incomplete information. And this SCASP system, that if you go to my homepage, you'll see lots and lots of applications and papers around it, implements it in a practical way that emulates human common sense reasoning. So reasoning actually has inherent limitations. So people have done, computer scientists have done, and mathematicians have done research on how far reasoning can go. And reasoning has inherent limitations, what is known as undecidability. There are things that you cannot prove, and also incompleteness. So even though things may be true, you can never prove them. That's the famous Gödel's incompleteness theorem that many of you may have heard about. So what it basically shows is that our reasoning capabilities are limited. So even if you automate it, the automated system will also have some limitations that it cannot basically prove anything that is provable or anything that is true. So the best we can do with respect to achieving, I would say, artificial general intelligence is to emulate collective human wisdom. So certainly an all-knowing AI that supersedes human capabilities, or what's known as artificial superintelligence, is not achievable in my opinion. So answer set. So let me just talk about some applications that we have built, that other people have built using this automated common sense reasoning engine, and the framework that I showed where you convert sensory information into knowledge, and this knowledge is processed using a reasoning engine. So one of the first application we built is this congestive heart failure treatment system, where the way congestive heart failure is treated, so another 3-4 minutes I should be done, is that there are some 80 to 100 guidelines. There's a huge document that American College of Cardiology has come up with. You can Google it and find it. There's also a link on my homepage. And then basically cardiologists are trained on these guidelines. Essentially, they're supposed to follow these. So these guidelines are basically rules that saying, if you're taking this medicine and that medicine, you cannot take that medicine. And if you have so much ejection fraction and this and that, then you cannot do this. So these basically these constraints and restrictions that you have to observe. So we actually automated this using our system. This is many years ago, and we worked with doctors at UT Southwestern nearby. And we actually were able to show that the system can outperform cardiologists, not because it is smarter than them, because it's basically working off the same knowledge that they are, but it's because as humans we make mistakes, right? We may forget that the potassium value, in the lab work that was done, the potassium value changed from 4.9 to 5.1, and now that triggers a different guideline. So it basically was able to outperform, but it's emulating exactly the same process that cardiologists are following. And in fact, this technology actually has been taken up by a Finnish company, and they're using it for automating the treatment of chronic diseases. So they built a system using our SCASP engine, and it actually has obtained approval from the equivalent of FDA in Europe, and they're actually selling the system. And so right now it's for managing the treatment of people who take schizophrenic people who take clozapine, but they're working on management of high blood pressure and diabetes, and it's going through the approval process. So common sense reasoning technology actually in action. Also, we've done projects with companies where we use this model to extract medical codes from electronic health records. So that's a huge problem, right? That how do you automatically extract medical codes from electronic health record, the description that the physicians write. So we use the same model. So if you use a large language model, then it's only 60-70% accurate, because large language models get confused. So how do we process it? We look at the text, we extract the knowledge, and then maybe we'll apply some rules to figure out the code. And that's exactly what the system does. So we built it with a company in Dallas called Coro Health. It's about 13,000 people company, where a lot of people are actually just manually doing this stuff. So you can actually achieve 100% accuracy just like a human would. We also built reliable chatbots that can understand human dialogue, so we built task bot, social bot, all kinds of things. And in fact, we worked actually with the Center for BrainHealth for automating the coaching process, right? Some of you use the coach, right? So we could automate that, but somehow and then other applications, system assurance, automating legal reasoning. So our system was used for actually finding error in Singapore law. Autonomous driving. So if you think about autonomous driving, the reason it doesn't work so well, works pretty well, but you cannot use it 100% of the time, because it's primarily based on machine learning. But when we drive, we're actually using reasoning, right? We look at, say, oh, there's a zebra crossing, there's a pedestrian standing, I must stop. So you have a rule in your mind. So if we combine, we look at the scene, we convert that into knowledge, and then we use rules to make, driving decisions, then, you can actually match human capability. For example, you cannot take an autonomous car that has been trained in US and put it in Germany and expect it to, function well. But as humans, we're able to actually, right, we know how to drive in US, we can go and drive in Germany as well, right, after quick learning, a little bit of learning. So that's basically the press release with Coro Health, where we use combination of learning and reasoning to attain near 100% accuracy in extracting medical codes from. And then I want to show you this reliable chatbot, and then I'll stop. So building chatbots that understand. So the idea is that when I say something, right, or when you say something, you and I are talking, then I extract the knowledge from the text, and then I process this knowledge, and then I compose my response based on this knowledge. So now that we have these large language models, we can actually use them for converting text into knowledge, represented as predicates. And since you can think of that as translating a language, that's purely a pattern matching process, the accuracy is actually quite high. So the idea is that, so for example, we build this chatbot that will actually, you're at a hotel and you go to the concierge and ask for a recommendation for a restaurant. If you ask ChatGPT, it might tell you a restaurant that's far away, or it might digress onto various things depending on how the conversation goes. But here, what you try to design is first you design an ontology, basically the predicates. So you kind of agree, these are the things that you and I should understand, and what are the things that I should know if I have to advise which restaurant you should go to. I should know that there's a concept of restaurant, they have a name, there's cuisine type for each restaurant, there's price range, whether it's family friendly or not, and then you might have a preference, you like sushi. So there are a bunch of predicates that I have to design so that again representing the knowledge that we need, and then I have to represent common sense knowledge, which of course includes database of local restaurants. And then I have to have rules saying, essentially, for example, if you say I prefer curry, then I'm going to recommend an Indian restaurant or a Thai restaurant for you. Or if you say I like sushi, then I recommend Japanese. So this knowledge actually can be quite vast. And then we can train a large language model to extract this knowledge from the text. So for example, if the guest says, I'm looking for a restaurant that serves curry, then the LLM will extract that you're looking for the name of a restaurant and your preferences. So again, these are represented as predicates. And then knowledge about finding a restaurant is also coded. So that's part of our common sense knowledge. So essentially, we'll know that to recommend a restaurant, I need to know the preferred cuisine, price range, family friendliness, and this is implemented in our system. Now, if you think about how humans converse, we give variable amount of information. So I might say, I'm looking for a restaurant, or I might say, I'm looking for an inexpensive Chinese restaurant, or I might say, I'm looking for an inexpensive Chinese restaurant for, my son's birthday party. So we're giving variable amount of information. So in the last case, I'm basically I'm indicated the price range, the cuisine type, and whether it should be a family-friendly restaurant or not, because it's my son's birthday party, right? So we extract this knowledge, and then we figure out what is missing, and then we ask that question, right? So you see how this works? So that's exactly the process we emulate. And then for every recommendation, you can actually give an explanation. You can ask, why did you recommend this? And it'll actually explain to you. And then, so the reasoning engine works, in the back end, and it produces a predicate response. Then we use LLM in reverse to convert this predicate into text. So here is a conversation. So you can see that the first bot says, hi there, how can I assist you? User says, can you recommend me a restaurant? And then it extracts the predicates. And then the conversation goes on, it keeps extracting predicates, and in the end and at any moment you can also say things like, you scratch that, go back to this. But all this has to be, again, programmed in your common sense, knowledge base. And that's like, you're training a concierge to recommend restaurants. Now, the interesting thing is that if you ask this bot something else, like, where is the restroom? It doesn't know anything about restrooms. So it'll say, oh, I don't know. I cannot help you with that. So you can also bound. Basically, it will not hallucinate, right? But now the downside is that, of course, you have to represent all this knowledge. So scalability becomes an issue, right? And I think, unfortunately, that's where the problem is. If you make it scalable, like large language models make it, you can ask anything, then you get this hallucination. But if you want to make it reliable, then you have to represent the knowledge against which you will check. So sort of your trusted knowledge base against which you can check the responses, and then scalability becomes an issue. But at least, we can build applications, narrow applications, that behave as well as humans. So for example, this technology is being used by a company for building chatbots, exactly the same method for counseling parents of ADHD kids. So we can, now it's very important that you don't give wrong information, you don't hallucinate. So you can actually restrict, you can be certain, and you're able to explain. So phase 1 worked very well, and now they're on to phase 2 and commercialization and stuff like that. Okay, so to conclude, so machine learning and generative AI are impressive technologies, but they're pure pattern matching devices with no correctness guarantees. We want to address the problem of developing reliable AI systems, and we essentially argued that reasoning is indispensable, and the corollary of that is that we don't have to worry about the singularity or AI taking over. The best it can do is match the collective human wisdom, and even that is a goal that is very hard to reach. So for building these reliable AI systems or reaching artificial general intelligence, we should use machine learning to convert sensory input to knowledge, and then use these reasoning engines for processing this knowledge to draw conclusions. And then our work, we build these. So we actually know, so that's quite a big advancement, because people didn't know how to automate common sense reasoning in a practical way. So this CASP engine actually is part of many big systems that are very popular, and many people are actually using them for building you could say AGI type applications, where you want the system to be able to perform as well as a human expert. And so it has been applied to solve many problems, including in the industry. So actually we're currently investigating. So this CASP system shows how we can model, right, human-style common sense reasoning. And we can actually, so one of my PhD students showed how we can represent these programs as graphs and execute this graph representation to get answers. So I really want to see, can I represent them using neurons? So then, of course, my argument would be that the mechanism in the brain for reasoning is very similar. So again, that is work in progress. So thank you. And then a lot more information on my homepage, and there's my email address. So sorry, a little bit more time than I should have. But questions? Okay. All right. So.
Hello. So a friend of mine, very, very good, funny guy, he once told me that computers will never be able to reach our level of intelligence or even surpass us, because they will never be able to achieve true randomness. By true randomness, I mean a lot of the stuff that you mentioned, like the sensible things, intuition, consciousness, etc. So my question to you is, what do you think so far, based on your experience, has been the best way to approach those true randomness capabilities that we humans have? How can we give that to computers? And as I'm saying that, I'm thinking perhaps virtual reality could be an option that we can maybe give those experiences to the best algorithms, and then they'll be able to actually think more like us.
Yeah, so the challenge, I think, is that oops, sorry. Oops, go back. Yeah, no, sorry. No, this was, I had my hand in the, yeah, so we're basically saying, well, can we represent sort of agency on a computer? I mean, so that's, yes, I mean, you can model that, but you have to figure out what kind of agency you want. So it's possible. I mean, if you say you want to represent an agent that is always selfish, I can program that. But you have to sort of tell me. So it's possible to. So you're absolutely right. I mean, you could design the virtual reality environment where something is happening, and then you want a certain type of behavior. You can actually program that. So as long as you tell me what you want, it can be programmed to the level of how a human would behave using the technology I described. So you could actually build, you could emulate personalities, for example. So for example, you might say, well, can I emulate the personality of Kim Jong-un? And then if some input comes, then make a decision that Kim Jong-un would, for example, make, or any person you choose. But then we'll have to model their personality and how they would react in a certain situation, model emotions. I think all that is possible. It's doable, I believe.
Okay, Gopal, we wanted to get to at least one online question,
Sure.
so I'll do my best to represent it. You've talked about how System 2 rule-based reasoning could be automated. What are your thoughts on maybe better modeling of intuitive inferences? And I think the spirit of this question is, can we see LLMs that will offer us good intuitive advice, and how would it maybe frame it so that we know it's an intuitive analysis?
Right. So intuition is basically, I would say, system one thinking, and for that you have to train a model, I would say. Right. So, but then of course you can use system 2 thinking to check your intuition, and your intuition may be right, or may be wrong. Yeah, but certainly for intuitive reasoning, you have to build a model, and yeah, LLMs might be able to give you that. That's possible, because this intuitive thinking is embedded in the text, and it may be able to use that to give you that response.
All right, well, we're at time, so thank you so much, Dr. Gupta, and I feel like we've glimpsed the human behind the curtain in Oz today. I've taken a lot away from this, I'm sure you have also. So let's go ahead and thank Dr. Gupta once again.
Thank you, thank you.
And we'll see you back here next week for our next
all right.
presentation. Thank you.
Thank you.